Okay, today we're going to talk about a different type of design using CMOS circuits. In particular, it's going to be called GM over ID method, which is a lookup table-based method. So the first thing we're going to do is look at the types of models we have for MOSFET transistors. We generally use a model that's called a BSIM model, and these have versions ranging from 1 to 4 to nowadays with specialized processes like FinFETs and SOI transistors, there are sub-versions of the model. But if we look at this, we can see what the particular challenge is. So the level 1 model is fairly simple. Here we have an NMOS model and a PMOS model, and each of these models only consists of 16 parameters. You can see all the parameters here. And you can see some of the familiar parameters that you might recognize, like lambda, the mobility, you might have seen, the oxide thickness. So these are physics-based parameters. These have to do with the operation of the device. Now, if we look at a modern BSIM4 model, you can see that there are a lot more parameters. They build upon the original BSIM1 base parameters, but there are both physical parameters and quasi-physical parameters and non-physical parameters at all, where the non-physical parameters are just being used to help to curve fit the device's performance with respect to the voltage and currents that are flowing through it. So we need to find a way to design knowing that the transistor's performance doesn't behave as predictably as it did when we were in the square law regime, and that our model has grown in complexity to where we don't have simple relationships to equations that we can use to calculate the performance of the device. So for instance, the BSIM4 model doesn't necessarily have mu or lambda or a simple threshold voltage that you might find in the BSIM1 model. We needed to find modified ways to approach the design algorithmically to replace our square law understanding of how the device works. And so one of the ways that we're going to do that is to look for ratios that don't depend upon the geometry of the device. So for instance, I could use the ratio of ID over W. Here I know that ID is equal to mu n C ox times W over L times VOV squared. I forgot a factor of 2 here. And if I divide this all by W, then to a first order, the W cancels, and there's no dependence on geometry. I could find another one. So for instance, here is our classic GM over ID. So GM over ID is equal to 2ID over VOV. I divide this by ID. This also ends up having no dependence on width. So again, I'm getting rid of the geometric challenge. The GM over ID is a favored metric because it tells us how much power we need to get for a given transconductance. So the units of GM over ID are Siemens per amp, which is equal to volts inverse. And if we have something like a GM over ID is equal to 10, this tells us that we need 10 microsiemens costs us 1 microamp of current. So it's scalable, and it tells us if we need a certain GM, it's going to cost us a certain amount of power. Okay, so let's look at how the square law diverges from reality. So our prediction of the square law tells us that if we were to plot GM over ID on a graph, and we know that GM over ID is equal to 2 over VOV, that tells us that as VOV approaches 0, our GM over ID tends towards infinity, and then it goes down as a square, as an inverse of the overdrive voltage. In reality, though, it doesn't predict what happens if we have very low values of VOV or even negative values of VOV. And in reality, our device behaves something more like this. And this regime where VOV is less than 0 is called subthreshold. And we can also say here that the transistor is weakly inverted, so we call this a weak inversion. Over here, where the transistor, a real transistor, is behaving like the square law, we call this strong inversion. And we have this regime for very small voltages where these curves are, kind of diverging. So we're going to call this region moderate inversion. All right, so let's ask why the square law breaks for very small values of VOV. So the first reason that it breaks is we have leakage current in the subthreshold operation. And we also have what we call short channel effects. And in particular, what we mean is the transistor is only supposed to be controlled, its conductance level is only supposed to be controlled by the gate voltage, in other words, the vertical electric field. But in reality, the drain voltage influences the vertical electric field because the transistor is so small, and it leads to things like DIBBLE, which is drain-induced barrier lowering. Additionally, in order to regain control of the channel and to make it perform the way that we expect it to as a transistor, over the years, they've had to dope the channel, and so they increase other physical effects that cause us some problems. Now, as a way to try and get control of the channel back, they have introduced FinFETs recently, and increasingly they're going to what are called wraparound gates, and I have some 3D drawings of these things right now. Fundamentally, what's happening at really low voltages and in the subthreshold region, though, is that the current mechanism in a MOSFET is supposed to be dominated by drift, but what we see is that the current mechanism is changing from a drift mechanism to a diffusion mechanism. And we know that bipolar transistors like BJTs are diffusion current dominated. And so what's happening ultimately is the transistor is starting to behave less like a drift-based device and more like a diffusion-based device, or we can say less like a MOSFET and more like a BJT. Okay, so let's look now at the square law of a MOSFET and start to make some predictions, or at least start to make some projections about the square law versus reality. So here's the traditional square law of a MOSFET. I have the square root of the drain current plotted versus VGS, and you can see that it should be 0 up until we reach the threshold voltage, and then the current, the square root of the current, will start increasing linearly. This is because this is a square law device. And this leads to a linear GM as well, the slope of this line. Now, the reality of this is that the current does something more like this. We have some current in subthreshold, and then the current will start to saturate for high values of VGS. So the current does exist in the subthreshold region below VTH, and then it does saturate as VGS increases. So if we go back now and think about this compared to a bipolar device. So we said on the prior slide that a real device is GM over ID, a real MOS device is GM over ID. It looks something like this. What about a BJT? A BJT has a GM equal to IC over VT. So if we find GM over IC, it's equal to 1 over VT. Now this doesn't depend upon the gate to source voltage or the base to emitter voltage at all. So in fact, the GM over IC for a bipolar device is a constant value. And so we see some divergence between the subthreshold region where we have a relatively constant value. If we look at the MOS device, it starts to kind of look like a constant value. When we get into the moderate inversion region, there's no way to predict what's happening. And then at strong inversion, the device starts, the GM over ID starts to match our prediction of square law-like behavior. So let's go and look at subthreshold operation just a bit more carefully. So here in subthreshold operation, we note that our simple model says no current is going to flow, but in reality, some current is going to flow. And in fact, we can predict what that current is given some characteristics about the capacitance in the device. In particular, we have this subthreshold factor, which is a non-ideality factor, and it is device dependent. This depends upon how they construct the device, how they dope things, etc. You can see more or less that the drain current in the subthreshold region will be equal to W over L times IDO times E to the VGS minus VTH over N times VT. Now that starts to look like a bipolar current. Times 1 minus E to the minus VDS over VT. And the parameter IDO is a device-dependent parameter. If the drain to source voltage is big enough, in other words, we can make this exponent go to a very small value, then this circuit behaves like a forward active region bipolar junction transistor. Okay, so let's now again start looking at that comparison of weak inversion to square law. So we know that in in weak inversion, our MOS device is going to behave for very small values of VGS like a BJT. So we have a more or less constant GM over ID. As we start to increase the VGS, these will diverge a bit, and as we get to big values of VGS, they'll come back together. So really what we need to figure out is what is the behavior in this region where we aren't behaving like we're in weak inversion and we aren't behaving like we're a square law device, in other words, in strong inversion. What's happening in other words, moderate inversion. So in moderate inversion, we have both drift and diffusion currents. and the ratio of these currents is approximately given by the following: VGS minus VTH over KT over Q. So this is our drift current relative to our diffusion current. There's no simple expression that tells us exactly what GM over ID is in this region. We know we have both elements of the current, drift and diffusion. So we're going to come up with some other figures of merit that are going to help us to figure out a way to algorithmically design amplifiers. And we're going to look at those in today's lecture, and then we will look at how we use them in an upcoming lecture. So the first figure of merit that we're going to look at is something we call the transition frequency. So we denote this as Ft, and this is the frequency where the current gain goes to unity. Now we know for a MOS device, the current gain should be infinite at DC, and then it's going to go down at 20 dBs per decade. And at some point here, it will cross the 0 dB line, and the frequency that it crosses at is Ft. Now, why is this a good figure of merit? Let's look on the next page. All right, so here I'm using omega t. I'm just noting that this is radial frequency instead of linear frequency. So we have that Ft, or omega t, is equal to Gm over CGS, which is approximately equal to 3 times mu times VOV over 2 times L squared, or a square law device. Now this tells us that as we shrink the length of the device, that it should increase its Ft by a factor of 1 over L squared. So if I shrink the length by a factor of 0.707, then it should double the speed of the device. In the GM over ID based method, omega t is defined a little bit differently. So we define it as GM divided by CGG, where CGG is the total gate capacitance that the device has. So this would be GM divided by CGS plus CGB, the gate to bulk capacitance, plus CGD, the gate to drain capacitance. Now, CGG is also equal to the charge derivative of the gate with respect to the voltage at the gate. So charge derivative at the gate with respect to voltage at the gate. Now this doesn't tell us anything other than how much gate capacitance we get for a given GM. It's not directly giving us anything related to the speed or the transition frequency of the device, but it is a metric that is independent of width. Another metric that we might care about is intrinsic gain of the transistor. So here we have a simple common source amplifier. We can say that the voltage gain, V out over V in, is equal to minus GM times RO in parallel with RL. And if we take the max of this, the max of VO over VI, it's equal to minus GM times RO, which is equal to GM divided by GDS, where GDS is the same as our output conductance, GO. Now for a square law device, we can say that GM RO is equal to 1 over lambda times GM over ID, which is equal to 1 over lambda times 2 over VOV. What if instead of a load resistor, we used an active load, a PMOS device acting as a current source? In this case, we would have a voltage gain equal to GM in the GM of the NMOS device times RON in parallel with ROP, the output resistance of the NMOS device in parallel with the output resistance of the PMOS device. And we can modify this expression a little bit and normalize it to the gain of an NMOS device in parallel with the gain of a PMOS device. And ultimately, we can then multiply by 1 over GM over IDP, and we can find the ratio of GM over IDN to GM over IDP to be roughly a factor of 2 to 4. This is primarily given by the ratio of the mobility of the device. Now we also care about saturation in the device. This is sometimes called VDSat or VOV. And if we have a square law device, we know that the saturating characteristic looks something like this, but oftentimes we estimate the saturation voltage as a constant value known as the VDSat. If we have these three curves, we could find the GM over GDS for these three curves, and they would be as follows. Okay, so let's look at VDSat and strong inversion versus weak inversion. So we know the square law of a MOSFET. We have GM is equal to mu times Cox times W over L is equal to VGS minus VTH. And we know that we sometimes call this VDSat or VOV. We also know the square law current, and we can find the GM over ID by taking the ratio of these two to be 2 over VGS minus VTH, or that's the same as saying 2 over VOV. And indeed, we could just take 2 divided by GM over ID and find that that's equal to the saturation voltage. Now let's look at what happens in weak inversion. In weak inversion, we know that our drain current is equal to ID0 times E to the VGS minus VTH. Sorry, VGS minus VT, the thermal voltage, divided by N times VTH, the threshold voltage, quantity times 1 minus E to the minus VDS over VTH. And we typically expect VDS is equal to 3 to 4 times VTH. And that's making the exponential term get very small. We can find the GM by taking the derivative with respect to VGS, and this would be ID O over N times VTH times E to the VGS minus VTH, sorry, VT, V thermal, that again, over N times VTH, quantity times 1 minus E to the VDS over VTH. And if we take the ratio of these two things, we find that GM over ID is equal to 1 over N times VTH. And ultimately, 2 over GM over ID is equal to 2 times N times VTH. Or about 3 to 4 times VTH. And that's, the same essentially is finding the saturation voltage for weak inversion. All right, so let's look at our metrics again that we've been considering. So we have transconductance efficiency, GM over ID, and the square law. We know that this is equal to 2 over VOV. GM over CGG in the square law is equal to 3 times mu times VOV over 2 times L squared. And lastly, we have GM over GDS, the intrinsic gain, is equal to 2 over lambda times VOV for a square law. Okay, so now let's look at some trade-offs. Let's look at GM over ID and FT versus VGS. So we're going to see what happens as we start to overdrive the device more. So we know that in weak inversion, the device has a big GM over ID, and in strong inversion, it has a small GM over ID. So our inversion characteristic goes something like this. On the other hand, the FT, which is kind of the speed measurement of the device, in weak inversion, it starts off slow and the device gets faster as we overdrive the device more, ultimately saturating. You can also find the product of GM over ID times FT. So if we multiply these two curves, what we would see is a curve that looks like the green curve here. And we'd have regions of weak inversion, moderate inversion, and strong inversion. So the peak GM over ID times FT, the peak gain efficiency versus speed happens for a GM over ID that's in the moderate inversion range of about 10 to 15. So typically a good trade-off for many designs is to begin operation in moderate inversion, and if you need the device to be faster, you can try and go more into strong inversion, or if you need it to be more efficient, you can go more into weak inversion. Now, the next thing we need to figure out is how do we actually use the GM over ID methodology? And I would propose a method that goes something like this. You can pick a length that gives a high enough voltage gain, and then choose a GM over ID so that the FT, the transition frequency, is high enough for maximum device frequency. And then you can calculate the device width using a ratio of ID over W, which again is another dimensionless ratio. So for instance, we might start off with a specification in the old method where we had a square law and we used a hand calculation. We designed a circuit. We put it into SPICE that used some models. We check to see, does the device meet the specification? If it doesn't, we go back and redesign the circuit. And if it does, we consider the design done. Now our problem, as we've said all along, is that the square law doesn't map any longer very well to our models that we're using. And so this ends up causing extra iterations in the design that we probably don't need. So a better approach is to start with a spec. We use models and SPICE to create lookup tables. And from those lookup tables, we feed into a hand calculation. And then the rest of the process is the same. Okay, so an example of how we might use something like this is, let's say we have a design that we know we are going to need a voltage gain, say, that's greater than 100. We have GM over GDS plotted against GM over ID for several different transistor lengths. So for instance, length going from 50 nanometers up to 1 micrometer, and length is increasing as we go in the upwards direction. So we know that we are going to need to pick a design, pick a GM over GDS that's bigger than 100 if we need to achieve a gain of 100 finally when the circuit design is done. So we could arbitrarily say that we want to operate at a GM over ID of 10, which would put it in the moderate inversion ballpark. And If we did so, we could then pick a GM over GDS that was greater than 100, so say 200, and that would tell us how long the device had to be in order to ensure that we would be able to get that gain at that particular GM over ID. Now similarly, we might have a speed or a bandwidth requirement. So here I have FT plotted as a function of GM over ID. So again, we're looking at this factor, this GM over ID curve. And so we might say have a speed requirement that says we need to be faster than 20 gigahertz. And that would set, the value of L that we would choose. So we might indeed choose this L, which I think is something like 100 nanometers. Now, after that, we know what our L is. We can start trying to figure out how to size a device. So again, from my tables, I have ID over W, the ratio of the drain current to the width, as a function of GM over ID. And I'm working at a GM over ID of 10, so on this line. And if I know, if I pick that GM over ID and I know the GM I need, then that intrinsically tells me I know what the ID is, and so then I know what W is. So once I know GM over ID is a function of, or ID over W is a function of GM over ID, I can size the width of the device. And then I can go back and check other parameters. So for instance, what the total device capacitance is, and I can use this to find FT. So generic design flow for us looks something like we pick a GM. This might come from design objectives. So for instance, for a two-stage op-amp, the gain bandwidth is proportional to GM over the compensation capacitance. The slew rate is equal to the tail current divided by the compensation capacitance. And I tail is going to come from the power specification. So this is going to help us pick GM. We could pick an L. Shorter channel means faster device, longer channel means higher gain. Then we pick a GM over ID. Large GM over ID means low power but slow. Small GM over ID means faster but higher power. And then we can determine our ID by dividing GM by GM over ID. Determine W by dividing ID by ID over W. And that has our devices sized. Now, there's no absolutely right or wrong procedure when you're using this method. There are some methods that maybe work more efficiently than others. And one thing to think about is that though this is a tabular-based method and it's separating the a physical model and intuition from our design process, it is still an algorithmic process that is not simply playing around or fidgeting with the size of the devices. It's an intelligent way to do the design. All right, so we're going to stop there for today, and we'll see you next time.